Hi viewers, welcome to my class on mechanics of materials. In this class, I'll introduce the different types of columns based on its end conditions and also explain the reasons for buckling, and will derive Euler's equation for buckling of columns. Column is a structural member basically designed to take up axial compressive load. So usually a column takes up axial compressive load. It may be subjected to lateral loads or loads acting in the sideways, but usually the major part of the load will be in the form of compressive load. And that is the main purpose of a column, which has to support huge compressive load. I'll explain 4 types of columns based on its end conditions or how they are supported at the ends. So first one is column with both ends hinged. Hinged means pinned. They are fixed in position but not fixed in direction. It can rotate at the hinged end. The column can rotate like this at the hinged end. They are fixed in position. The column end cannot move, but it can rotate. So in this case, both ends are hinged. So both ends are fixed in position but not fixed in direction. So that way also you can state this type of end condition. Both ends are fixed in position and not fixed in direction. Now second type is both ends fixed. The column is fixed at both ends. So there is no rotation allowed, no movement allowed. So it is fixed in position and direction. So it is fixed, both ends are fixed in position and direction. So you can say the column with both ends fixed or both ends are fixed in position and direction. Now other type is one end is fixed, the other end is free. So this end is fixed in position and direction, the other end is not fixed. So it is free to move. Even that end A can move sideways. So it's not fixed in position or direction. Now fourth type is one end is fixed, the other end is hinged. Both ends you have different kinds of support. So one end is fixed, so fixed in position and direction. The other end is hinged. Hinged means fixed in position only, not in direction. So these are the commonly occurring end conditions for columns. Now when columns are subjected to axial loads, they get compressed. So normal compressive stress will be acting, and the length of the column will reduce. That is common when it is subjected to a compressive load. But when it comes to the long columns, it is likely to bend the column sideways like this. Okay. The bending occurs, and this bending is mainly due to the imperfections in the column existing at the starting of the. So when a column is built, there might be some imperfections, like the axis may not be perfectly straight, or maybe due to slightly eccentric loading. The loading may be applied slightly away from the axis. So these imperfections and loading conditions may leads to buckling of columns, and for short columns they do not buckle. Even these exist in these columns, load eccentricity or imperfections exist in the column also. The short columns will never buckle under compressive load. It only get compressed and fail. But long columns can buckle, and due to excessive load it can buckle, and sideways it can bend, and bending will induce excessive bending stress in the member, and this bending stress along with the direct stress induced due to the load can be beyond the permissible limit allowed in the material, and the column may fail at a very low load compared to the normal failure of the column due to normal compressive stress. So this is very critical in case of columns because the column may fail at a very less load. So we need to analyze these type of columns and find out the load at which the column fails. So Euler's gives a theoretical load at which the column buckles or cripples for all these n conditions. So Euler's formula gives a theoretical buckling or crippling load for long columns. We'll see what is the formula for crippling load or buckling load of these columns given by Euler's formula. Let us start with a column with both ends hinged and subjected to an axial compressive load. Now I have shown that buckling of the column in the sideways, and let us take a cross section. At a distance x I am taking a section, and this is initial before applying the load, and after the column buckles it takes a position like this. So at a distance x there is a lateral deflection, and this horizontal distance is y, so there is a deflection which is y. The differential equation for the deflected elastic curve is given by ei d square y by dx square is equal to bending moment. Now the bending moment acting, that is moment acting at this particular section is p into y, and that is anti-clockwise. So this with respect to this point, p into y, that is py, is anti-clockwise, so I written it as minus py. So ei d square y by dx square is equal to bending moment, you can write it as minus py. And you can also observe that shape of the deflected curve. You can see that it is bending like this. It is not straight here. So there is a slope at the starting point also. At the hinged end also there is a slope for the deflected curve. Here also there is a slope. Slope is not zero. It is not straight. Okay. So this is a deflected position. We know ei d square y by dx square is equal to bending moment, and bending moment we have seen that it is minus py, or taking that minus py to the left hand side you will get ei d square y by dx square plus py is equal to 0. So you can divide this whole equation by ei, you will get d square y by dx square plus p by ei y is equal to 0. Now replacing this p by ei by m square, or m is equal to root of p by ei, you will get d square y by dx square plus m square y is equal to 0. Now solution of this differential equation is given by y is equal to c1 cos mx plus c2 sin mx. Now we know the end conditions, that is at this hinged end, that is x is 0, x reduces to 0, the length of the column is L. Now at this end x is 0, so starting from here I am measuring the distance. So at this end and the x is 0 and there is no deflection, there is no sideways movement because it is hinged, it cannot move. So the deflection y part is 0, so y is gradually increasing and it has a maximum value at the center and decreasing to 0. So we can immediately write x is 0, y is 0. So in this equation, in this solution, we can substitute y as 0 when x is 0. So when x is 0, cos 0 is 1 and sin 0 is 0. So you will get this equation and we will get c1 as 0. So the constant c1 is 0 in this solution. So you get when c1 is 0, you get the equation as y is equal to c2 sin mx. So y is equal to c2 sin mx. Now after getting this equation, you also know the condition for the other end. At this end, and that is when x is equal to L. When x increases to L, that is the maximum value of x can take. When x is equal to L, and the deflection is also 0. There is no moment. Y reduces to 0. In this equation, we can substitute y as 0 when x is equal to L. So what you get is C2 sin ml is equal to 0. Now in this case, C2 cannot be 0. C2 0 means already we got C1 as 0. So C1 and C2 0 means y will be 0. There will not be any sideways deflection at all. So C2 cannot be 0. C2 0 means there is no buckling, no deflection. So sin ml, buckling occurs only when sin ml 0. Sin ml has to be 0. Okay, this is the solution which we are getting. Sin ml 0, sin of a quantity is 0 when it is 0, pi, 2 pi, etc. So when ml is equal to 0, pi, 2 pi, etc., sin ml will be 0. But ml 0, you cannot take it as a solution. Ml 0 means m is root of p by ei. So ml 0 means p has to be 0. Without p 0, you cannot get the ml 0. So p cannot be 0. P 0 means the load 0 means it's not a solution. So least value of solution possible for this. The least load at which the column buckles is when ml is equal to pi. M is root of p by ei and L is equal to, if you equate to 0, then P should be 0 because L, ei, all that values exist. So P cannot be, P 0 means there is no point in analyzing the load. We are finding out the load at which the column buckles. So the least possible value at which the column buckles is when ml is equal to pi, or root of p by ei, L is equal to pi, or squaring it, p by ei L square is equal to pi square, or p is equal to pi square ei by L square. So this is the Euler's load for buckling of a column with both ends hinged. This is a crippling load or buckling load for a column with both ends hinged. It's for a long column, pi square ei by L square. The crippling load or buckling load for a long column with both ends hinged is pi square ei by L square. That's all for today. Thank you for watching.